What the heck?
Tagon.
Howdy, it's Fuzzy McHairyface coming at you. Hopefully getting a haircut and a trim in like a week. We are still trapped. Okay, so today is going to be the tantalizing and scintillating second part of my series of, I guess, lectures on the properties of tetration as a function, where we think of the base as the moving thing as opposed to the height of the tetration. In the last video we covered the inverses of the said power towers, right? And so today we're going to cover, and including those other functions, the epsilon functions, which were sort of the generalized version of x times e to the x, and the omega functions, which were just generalized versions of the Lambert W function, namely the inverses of the epsilon functions. And we were able to discover a way of putting the inverse of the tetration functions, or the power towers, the pure power towers, in terms of these omega functions, precisely one omega function down from the power tower that you're on. And today we're going to derive the derivatives of these functions and see what nice identities they give us. This is sort of just a purely mathematical foray into something kind of fun and obscure that doesn't really have a lot, I would say, necessarily a lot of application. And eventually I will be getting to the super logarithm, because I understand that people want to talk about those too, because that's an interesting inverse. You know, I'd say the logarithm is the more interesting inverse compared to the root when it comes to exponentiation. So perhaps the super logarithm will be more interesting than the super root, but for now we're just focusing on those. So let's get right into it. We're going to do the derivatives of the tetration function, the epsilon function, and the omega function, and see what cool facts we can derive. Okay, so the function that most people would probably find the most interesting out of these set of three types of functions, tetration, epsilon, and I'll just say t, epsilon, and omega. Probably the omega functions would be the most interesting, because they're a generalization of this sort of mysterious function, the w function, which is sort of in particular, a special function that I've been doing a lot of videos on recently, which you should all check out. And so we might ask, what's the derivative of those? It seems reasonable to ask that question. So if we said, what's the derivative of one of the omega functions? I don't know which one it is, but perhaps we can put it in terms of one of the lower ones, in which case maybe we could get a recursive definition, which is a good way to think about it. That's always a good place to start. But you might recall, so we'll say, what is this? We don't know. Put a little question mark next to it. But we might recall two facts. A, the first fact, or one I'll call it, is that the nth omega function is by definition the inverse of the nth epsilon function. Epsilon n of x is equal to specifically x times the nth tetration of e to the x. Right? It's a generalization in terms of power towers of the function that has w as an inverse. So the first tetration of e to the x would just be e to the x. It would get x times e to the x, and so epsilon 1 has the inverse omega 1, which is in particular the Lambert W function. And the other fact to know is that because they're inverses, this is how the derivative works. So we know that the derivative of this omega function is, at the very least, going to be the reciprocal of the derivative of the inverse of that, the nth epsilon function, applied at the nth omega function. Because that is how you take the derivative of an inverse function when you know the derivative of the original function. And I did a video on that quite some time ago, and I'll link to it now. And so, at the very least, this question about what to do with the derivative of the omega function can be reduced to, maybe we could answer this question instead. What's the derivative of the nth epsilon function? Because clearly, putting one, these are functions we understand more about because we can write them as a closed form, at the very least, right? They can get exceptionally huge and steep, but it's a closed form nonetheless, so perhaps it would be easier to find the derivative here. But because of this definition of the epsilon function, this comes down to being the same as the derivative of x times the nth tetration of e to the x. So we need to apply the product rule. So we need to take the derivative of the first term, which is 1. So that's going to give us t, the nth tetration of e to the x. And then we have to keep the first function and take the derivative of the second. So we'd get x times the derivative with respect to x of the nth tetration of e to the x. So of course we're also going to have to do the chain rule and take e to the x out as well, but essentially this is the problem here, right? And what does this hinge on? This hinges on understanding the derivative of the nth tetration function. So we're sort of peeling back the layers, right? If you want to find out more about the omega function, it does you well to understand more about the epsilon functions, not surprisingly since they're inverses, which means it would do you good to understand more about basic tetration. And so we're actually going to come upon a closed, not a closed form, but a way of expressing this exact term right there. That thing. Because this, at the very least, can be put back in terms of the epsilon function, because what is this? This is just the nth epsilon function without that x on the front. So it's epsilon n divided by x. So we can replace it like this, epsilon n of x divided by x. And so, you might think, okay, well, we could just write this like that and then do that and cancel things, but then you sort of get right back to where you started, and it doesn't really work. At least that's what I think would happen. Feel free to try it by turning this into epsilon n of x over x and taking the derivative, but I imagine it would probably cancel things and you would just end up with a trivially true statement, a vacuously true statement. And so it's going to come down to understanding what this term equals, because this can be put in terms of the function we're taking the derivative of, which is perfectly fine for, say, like a differential equation. And so what we need to fundamentally understand is instead the derivative of the nth tetration of x. What is this equal to? And this is really like the soulful, I wouldn't say soulful, the one that people, I guess I should take back what I said before. I said people care more about the w function, but these seem to be more mysterious, right? Like they're just these power towers of x. They look so simple and elegant, yet they're so hard to grasp once you get beyond, like, say, 2. The second power tower, that is. So instead of just diving right in and trying to prove it, let's actually take a look at some examples. So from the previous video, we learned that the negative first tetration of x, no matter what x is always 0. And the 0th tetration of x, no matter what x is always 1. So that tells us that the first two examples, so clearly the derivative of the negative first tetration is equal to the derivative of the of the 0th tetration, which is equal to 0. Cool. So that's a way to start the pattern. Maybe these don't really hold to whatever pattern we derive. Maybe they do, but the point is we know the answer. And then the next one is quite easy as well, because the first tetration of x is simply x, which implies that the derivative of the first tetration of x is simply 1, right? So not 0. And that's just about where it stays simple. I'm going to erase this line of reasoning here, and we're going to just start deriving the first couple. I'm only going to do the 2 and 3 power towers, like to prove what they are, and then you're just going to have to trust me on what comes after, and then I'll prove the relationship. But I'm going to write down like what some of the other answers are, but I definitely won't rederive those. So I'm going to do 2 and 3, and that's it. So let's see if we can derive the derivative of the second tetration of x. So let y equal the second tetration of x. So we have y equals x to the x, and if we want to take the derivative of something, we might want to put something in terms of logarithms. So let's take the log of both sides. So we get log y is equal to, now using the power rule, the power comes down, and we get x times the log of x. Now, of course, we can use implicit differentiation on both sides. So if we take the derivative of this, we get the derivative of the logarithm, keeping y inside, so that gives us 1 over y. Right, 1 over y, and then we have to multiply by the derivative of the inside, so y prime. We know what y is, that's x to the x, so we can write this as y prime divided by x to the x, and then we simply do the same idea here, but we have to use the product rule. So the derivative of the first part is 1, so we get 1 times the natural logarithm of x, and then we keep the first part and multiply by the derivative of the second part. But the derivative of ln of x is 1 over x. So x times 1 over x is just 1, multiplying x to the x over, and we have that the derivative of y, or the derivative of the second tetration of x, is precisely x to the x times the quantity, the natural logarithm of x plus 1. So that's quite a jump in complexity from the derivative of just the first one, right? So we need to sort of maybe do another example and see if we can see a pattern. So let's just write these up here. T2 times ln of x plus 1, the quantity, ln of x plus 1. So we've already got quite a bit of a jump in complexity. Right, so let's try to figure out the third tetration, the third power tower, and then I'll just state what the next couple ones are, and then we'll actually prove what the relationship is, what the recursion is. So Or not necessarily, I don't know if it's recursion, I should say. But let's see. So let y equal the third tetration of x, which is, of course, x to the x to the x. We should, again, start by taking the logarithm of both sides. So we get log y is equal to x to the x times log x. But now we can actually do this, because what we can do is just simply take the derivative now, because we know what the derivative of x to the x is. It's this right here. So let's take the derivative of both sides, again implicitly differentiating, so we get y prime over y, the logarithmic derivative of y. Now we have x to the x as our derivative, so the derivative of x to the x is x to the x times the quantity log x plus 1, right? That's what we just derived. And then we have to multiply by log x. Now we have to add x to the x times the derivative of log x, which is going to give x to the x divided by x, right? Now, if we factor the x to the x out, we end up with, and this y down here is, of course, x to the x to the x, because y is the third tetration, right? It's x to the x to the x. So we multiply that over, we get x to the x to the x, and then we can factor x to the x out of both of those things, like so. And then we're left with log squared plus logarithm plus 1 over x. So this is a very strange jump in complexity now. Now we've gone from this relatively tame-looking thing to this thing right here. So clearly there's some relationship with, say, the function itself and perhaps lower tetrations, right? And also powers of the log of x. But where's this 1 over x come from? Because, you know, it's sort of weird to see these two functions added together in that way. It's a little odd to see them combined in this way. But this 1 over x is sort of, I wouldn't call it an illusion as to what it is, but it's sort of confusing what the pattern might be. But I think as soon as we take a look at the derivative of the fourth tetration, which I'm just going to tell you, you might begin to see a pattern. So if we let y equal the fourth tetration of x, then the derivative of y, or the derivative of the fourth tetration, which is again x to the x to the x to the x, we multiply by the function itself, the fourth tetration, 1, 2, 3, 4. Then we multiply by the third tetration, 1, 2, 3. Then we multiply by the second, 1, 2. And now we have, in parentheses, logarithm cubed plus log of x squared plus log x over x plus 1 over x to the x times x. So a very strange derivative indeed, very much ramping up in complexity. But as we can see, we always end up with, what it seems to be, is we always end up with this product of these tetrations all the way down to the second one, right? And not including the first one, which is a little weird. But what we can do maybe is correct for that by simply plugging x in as part of the product at the end of all these, right? So just multiplying them all by x, right? But then we have to remember to divide by x as well. We can't just do that one thing. So we multiply by x, we have to divide by x as well, and you may think that's a little weird, right? You're complicating things. But now we have the full product of the first tetration up to the nth with regards to the derivative at the nth tetration of x. So here's 4, right, and we go up from 1 to 4. All we had to do was simply put an x in the denominator, and you'll see that this is actually going to be perfectly fine. And will actually help us understand what it is that we're actually looking at. But if you take a look under here, what's weird is that we have these powers of the natural logarithm of x, and then we start getting these factors of tetration powers in the denominator, which is a little inexplicable. But notice that the pattern is actually perfect, because we have log x to the first plus log x to the 0 power, because that would be 1. They're both divided by 1. And then we increase the powers of both of those by 1, still dividing by 1, and then the new one is divided by x, right? So it's log squared over 1 plus log over 1 plus 1, or log to the 0, over x. And then here the same pattern continues. Increase those two log powers by 1. We have log cubed over 1, log squared over 1, plus log over x, plus 1, or log to the 0, over x to the x times x. And so this may start behaving, let's just write those 1s in the denominator, this may start behaving as some sort of product of the power towers, just like these do, right here. And in fact, they do. But what we're going to want to do is define a particular function involving products of power towers to sort of compress this entire expression. So maybe we could write it in a generalized and nice compressed form. So let's write up these examples up top here. And here, I'll just write down the fifth one as well, just to show you that the pattern does in fact continue, because it's quite nice. We do in fact end up with x to the x to the x to the x to the x times the fourth one, x to the x to the x to the x, times the third one, x to the x to the x, times the second one, x to the x, and times the first one, x, if you're willing to divide by x there just to cancel it. Then of course we do end up with log x to the fourth over 1 plus log x cubed over 1 plus log x squared over x plus log x to the first over x to the x times x, and just like I predicted in the previous one, there does in fact become this 1 over x to the x to the x times x to the x times x. So that power tower thing does continue, and you can't really see that off the end, but the point is that I'm correct when I say that. And so we might have the hunch of trying to define what the arbitrary derivative, the derivative of an arbitrary power tower is. So let me just quickly write down the third one here for us to reference perhaps. And so that's the derivative there. And so based on our hunch that we've just been able to derive or think of, let's see if we can prove what the general derivative might be. So first we're going to want to define a particular function, and I'm going to call it capital T n of x. So n is another index, and this is simply sort of the factorial version of tetration. It's or the tetration version of factorial. It's the product from k equals 1 to n of the kth tetration of x. So this is a particularly fast-growing function if you go outside of a certain range. I'd love to know what happens as n goes to infinity, if any parts of it converge. That would be really interesting to understand, or know. But, so this is, if say we wanted t3 of x, this is simply just going to be the third tetration times the second tetration times the first tetration. So that would be x to the x to the x times x to the x times x. Clearly, if we wanted to get to the one next, we would have to multiply by the next tetration of x, sort of like factorial, right? Multiplying by the fourth tetration will get you the fourth product of these power towers, so we're multiplying by x to the x to the x to the x, right, to move on to the next one, which means to go back to the previous one, you have to divide by the current biggest power tower. So in this case, t to the third tetration, right? So if we divide by that, that goes away, and we're left with capital T2 of x, right? So if we want to move on to the next one, we multiply by the next tetration. If we want to move on to the previous one, we divide by the current tetration. So clearly, capital T1 of x is just x, right? Because it's just the first tetration of x. It's the product that goes from 1 to 1, so there's only one term. So let's see if it goes backwards. So T0 of x is of course just going to be, like I said, the next tetration divided by the current, or you want to know the product before, you have to go to the one after it and divide it by the current power tower in that instance. But we just determined that capital T1 of x is going to be x, and we know that the first tetration of x is also x, so that turns out that capital T0 of x is always 1. Let's see if we can keep going, right? That would mean that the negative first, t negative 1 of x, would be T0 of x divided by the 0th tetration of x, which is, of course, we know that T0 is 1 from our previous problem, and we know that the 0th tetration of x is always 1. So again, t negative 1 of x is always 1. And that actually helps us, because remember, in these derivatives that we started with, we always end up with two terms that are divided by 1, whereas we ending up with the power towers. It turns out, it will turn out, that these are in fact the negative first and 0th products of the power towers that are in the denominator there, which are both 1 for any x, and so the pattern will actually hold. So the hypothesis here is that the derivative of the nth tetration of x is actually equal to this nth product of the power tower. So capital T n of x, right? And it went from the first tetration all the way up to the nth, but we're going to still divide by x, because remember we had to make that x pop out of the equation to allow for the full product. We had the sum of powers of the logarithm. So let's start off at k equals 1, and we're going all the way up to n, right? And so remember, the powers of the logarithm go from 0 to n minus 1. Good thing, if we do this, we can put log of x to the power of n minus k, because k starts at 1, and n is n, so the first power is going to be n minus 1, which is the highest power, and then it's going to be n minus 2, and then it's going to be n minus 3, right, all the way down until you get to 0. So the highest k is going to be n, which accounts for all the powers of the natural logarithm. But notice that as these powers of the logarithm go down, the product of the tetrations go up. So we're gonna work with the assumption that perhaps there is the negative first tetration down there, or the negative first product of the tetrations and the zeroth product of the tetrations and the first product of the tetrations and the second. And we're just going to write in the bottom these products of tetrations, right, as part of it. But we need to base it on the index here. So since k starts at 1 and we have n terms in total, but we want to start at -1, we actually have to do k minus 2 as the index for this product of power towers, because we want to start at the negative first product and the zeroth product and the first product, etc., etc. So our goal today is to prove this relationship and then see what that tells us about the other functions. So what we might want to do, so let's assume for a second that this is true, and I can then transform this into other things. And a form that might actually be easier to prove is actually the general form. And we're simply going to use induction to prove it. It's really not difficult. It's just a little bit symbol heavy. So what we're going to do, actually, is because, remember, the nth product of the tetrations is just the n minus first product times the nth tetration, we're going to leave the nth tetration out here, and we're going to put the rest of that product, which is the product from m equals 1 up to m equals n of the tetrations, and put it inside the product here. So actually I'll leave that there, just so I can rewrite it here. So I'll leave the nth tetration, the nth power tower, outside, like so, just like that. I'm going to bring the rest of the product for this capital T function inside the sum. So we have k equals 1 to n, and now we have big T n minus 1 over x divided by big T k minus 2 of x times these powers of the natural logarithm of x, n minus k. Now what we can do is compress this into one product, right? So if we have this capital T n minus 1 is the product from m equals 1 to n minus 1 of each of the power towers of those heights. And this is the one from m equals 1 to k minus 2 of all those different heights. So if we divide this product, which goes from 1 to n minus 1, by everything that goes from 1 to k minus 2, we will then have a product that goes from k minus 1 to n minus 1. I hope that's clear. So we can rewrite this like so, and I'm leaving a space here for a reason. The sum from k equals 1 to n, and now we have a product from m equals k minus 1, because we're taking away everything from 1 to k minus 2, so that leaves everything from k minus 1 and above untouched. And then because we left the nth tetration outside, this product now only goes to n minus 1 as opposed to n, like before. Now let's find out how many terms there are here. So the number of terms is simply the top one, minus all the ones that we don't have anymore. So we have in this product, what we will have is n minus 1 minus k minus 2 terms. So if we do the difference, we get n minus k minus 1 plus 2, which is n minus k plus 1. So whatever this product is, it's going to have n minus k plus 1 terms, and that will be important. But what is this product? Remember, this is over the capital T function, which is a product of all the tetrations. So what we have here is the product from m equals k minus 1 to n minus 1 of the nth tetration of x. So it's going to be quite a large product of power towers that we have to deal with here. But remember, what do we have? We also have the natural log of x to the power of n minus k. But remember, how many terms in this did we say that we had? We had n minus k plus 1. So we're one logarithm short from being able to just put all of them inside this function here. So why don't we just do a little cheat and actually increase that power of logarithms by 1, but in order to cheat, we have to uncheat somewhere else, and so we have to divide by a power of the natural logarithm of x. But because log x doesn't depend on m or k, we can factor it all the way out and simply put it here in the denominator. Now what we can do, because there are precisely n minus k plus 1 terms in this product, we can now rewrite this product, this power of the natural logarithms, by simply giving one of those logarithms to each of the terms inside this product. And because there are n minus k plus 2 terms, that entire power of the logarithm will be accounted for, and now we can combine them like so. And so this is the relationship that we're going to prove. This is the equation that we're going to prove. That the derivative of the nth tetration of x is equal to the nth tetration of x divided by x times the logarithm of x times the sum from k equals 1 to n of the product from m equals k minus 1 to n minus 1 of the nth tetration of x times the natural logarithm of x. And feel free to work backwards to maybe see that this is exactly the same as this thing that we derived before. So we're just going to do simple induction, and one might think, let's start with the lowest example, like -1 or 0 for the tetration, for the base case. But both of those are rather boring because we're going to start a sum from 1 and go backwards to 0 or -1, and those are generally considered empty sums, and so equals 0 by default. We know that that is true, right? The derivatives of these functions are 0, but that's such a boring place to start. Let's see if it actually works for just the first one and use that as our base case. So the good thing about it is it's still something very easy, right? The first tetration is just x, and so the derivative is just 1. So let's see if this function here works for that. It'll actually turn out that this form is going to be more advantageous for later, by the way. So we're going to erase these two and simply rewrite it up here. I have myself a completely clear glass mug of Joe. Pretty amazing. He's a little scantily clad today, but we accept him nonetheless. So this is our derivative, or what we suppose might be the derivative of the general derivative for the nth tetration of x. A very interesting claim, very interesting looking, quite complicated, sort of in terms of functions that, you know, are sort of hard to comprehend a lot of the time, you know, these tetration functions, not to mention we have a product inside a sum of these functions, so it's quite complicated indeed, but let's see if we can prove it using simple induction. So we'll start with the base case, n equals 1, right? So we want to prove that the derivative of the first tetration of x follows from this fact that we've derived here. So the derivative of the first tetration of x, which, because the first tetration of x is x, we know that this should end up just being 1 in the end. So we're just going to plug 1 in wherever we see n, and see what we end up with. So we should get the first tetration of x, there, because we just plug in 1 there, divided by x times log x times the sum from k equals 1 to 1, right, of the product from m equals k minus 1 to 1 minus 1, which is 0, of the nth tetration of x times log x. And we'll see that this actually does simplify. So let's see. We know that k is going from 1 to 1, so there's only going to be one term. So we can actually just plug k in here and evaluate the product. So we don't care about that. We just need to plug in 1 for k, and the bottom index, which is m, is k minus 1. So 1 minus 1 is 0, which means we're simply taking a product from m equals 0 to 0, which is again one term in the product. So this is going to be the 0th tetration of x times log x. But the 0th tetration of x is 1, and log x is just log x, so this turns out to be the first tetration of x times log x, because the 0th tetration of x is 1, divided by x log x. The log x's cancel, and of course the first tetration of x is just x, so they also cancel, and we're left with 1, which is precisely the correct answer. And I know that's not monumental, right? This crazy complicated thing simplified to 1, you know, it sort of looks like it could just do that in any simple case. But as we can see as we go higher, they certainly don't stay simple. So we actually have to use induction if we really want to get anywhere. So what we're going to do is then assume that it works for some number, right? We've proven that it works for the smallest number, and now for the induction hypothesis, we're going to assume that it works for some number, and then prove that if that's true, we can show that it's true for the next number. And then we can just pick that some number that it's true for to be 1, which proves 2, which proves 3, which proves 4, etc., etc. So we're going to assume. By the way, just for simplifications, let's just call this wacky thing tau n of x, just so I can say. So I'm not saying that tau is the derivative of t. I'm saying that tau is this function which we are going to prove is the derivative of t. So we've shown that the derivative, what I'm trying to say is, say we've shown that the derivative of the first tetration of x does in fact equal tau 1 of x, right? Because plugging 1 into this equation gives 1, which is the derivative of the first tetration of x. So tau is the name of this function that we're going to prove. So this is what we proved for the base case, so n equals 1. Check. Assume, for the n equals, pick another letter, I guess. What's the letter we haven't used? P. So this is the n equals 1 case. This is the arbitrary n equals p case. So assume that the derivative of the pth tetration of x is in fact equal to this tau function p of x. Tau function p, tau at p, right? So it says tau p of x there. So essentially what we're saying is, if I were to take the derivative of the pth tetration of x, that would be identical to simply plugging in p wherever I see an n into this equation, and I would get the same answer. And now that we're assuming that, we're going to prove that given this fact, the p plus first tetration, the derivative of that function, is in fact tau p plus 1. So let's do that. So now we have to prove n equals p plus 1. Let's go. So we want to take the derivative of little t p plus 1 of x, right? And somehow in the proof of what this is, we want to use this fact that the derivative of the p tetration is in fact tau p of x. And so we need to somehow put this in terms of the previous tetration function, which is not too difficult. It's equal to x to the power of the previous one, right? So tp plus 1 of x is equal to x to the tp of x, just by the definition of tetration. And then we can use the exponential function to rewrite this as e to the log of this thing. So we get e to the p tetration of x times log x, because of the way powers work for logarithms, so that power of tp of x comes down the front. And now we can more easily take the derivative of this, plus we have it in terms of the pth tetration of x, which is what we want, as opposed to the p plus first, which is what we're trying to prove. So we take the derivative of this. Well, the derivative of e to the something is just e to that thing, so that stays. So we get e to the log x all to the power of the p tetration of x. And then we have to take the derivative of the inside, right? So the derivative of the inside, we would take, let's swap these. So we would take the derivative of the log function, which is 1 over x, times the p tetration, the pth tetration. So we get tp of x over x, right? That's that. And then we have to take, we have to keep the log x, and this is all being multiplied, right? We have to keep the log x and then multiply by the derivative of the p tetration of x. Which is good, because that's what we know already. That's the assumption, right? We are assuming that the derivative of the pth tetration of x is just this function evaluated at n equals p. Let's simplify our expression here. So this is tau, this is, remember, by assumption, this is tau p of x. And we're trying to prove in total that this is equal to tau p plus 1, right? So this is the same as this right here, which is the same as the p plus first tetration. So I can replace this with tp plus 1. I hope that's clear. Since this whole thing is tau p of x, which is by assumption equal to this equation here, I can rewrite it as such. So we end up, what I'm going to do first is before I do that, I'm going to factor some stuff out so we have a nicer equation, because I want to establish this term out the front first. So you notice that we already have the current tetration there, but I also want to divide it by x log x. So I need to factor x log x out of the denominator of both of these terms right here. So I'm going to end up with tp plus 1 of x divided by x log x, and that deals with the outside. And now, because I factored this x out, that's gone, but I also have factored out a log x from the denominator, which means a log x needs to appear in the numerator of that term there. So we get log x times tp of x. And now, because I factored out an x log x from something that doesn't have either of those in the denominator, I need to multiply the numerator by x log x here. So we get x log x squared times tau p of x, right? But tau p of x is this equation here. So if we multiply this in, we're going to end up with kind of a wacky looking thing. So we're going to get x log x squared times tau p of x. So it's getting pretty complicated, I understand that, but we're just about to finish the proof now, because now all we need to do is rewrite this as the general equation and show that it will actually simplify to the next one down. So what is tau p of x? Tau p of x is just this equation with p plugged in wherever you see an n. So we end up with tp plus 1 of x divided by x log x times the log of x times tp of x. Now out the front of tau p is going to be tp of x over x log x. So we have x log x squared times tp of x, now divided by x log x, which is good to see, times the sum from k equals 1 to p times the product of m equals k from m equals k minus 1 to p minus 1 of the nth tetration of x times log x. Okay, so that's the full expression now. Quite a lot, I know, but watch what happens. So the x's cancel, and the logarithms cancel. And we're left with log x times the p tetration of x. Since this product goes from the k minus first tetration of x to the p minus first tetration of x, this product of ln of x times the pth tetration will move this product up by 1. So we can actually erase all this and simply increase this product from going from p minus 1 all the way up to p. So I hope that's clear. That's step 1. But now, take a look at this. This would just be the p plus first term of this sum. Notice, if we were to plug in p plus 1 in for k, we would get m equals p plus 1 minus 1, which is just p, which means this product would range from p to p, which is equivalent to having a single term with the p tetration in it, which means that this is the p plus first term in this sum. So we can actually combine these all together like so. The sum from k equals 1 to p plus 1 of the product from m equals k minus 1 to p of the nth tetration of x times the logarithm of x, which is in fact tau p plus 1 of x, which proves this induction hypothesis, or proves the theorem that this is the true derivative of the nth tetration of x in its closed form for integer n. And this was the proof of that, right? So we proved it for the n equals 1 case, quite simple. We assumed it for an arbitrary case n equals p, and then we proved that if the p case is true by utilizing it in the proof here, by turning this into this, by turning this into this, which was equal to this, we were able to show that it sort of causes the dominoes to fall, and every case is actually proven. So this is in fact the derivative of the nth tetration of x. I'm not done, but thank you for getting this far, at least, if you have, because that was an arduous, very symbol, heavy process. But we did, in fact, do it. We proved it using induction. Even for these most complicated expressions, induction comes in handy. So let's see if now we can use that to inform the derivatives of those other special functions we have, which are the epsilon and omega functions. This is what we've actually derived. So we derived that the derivative of the nth tetration of x, which we lovingly called, oops, you can't see anything I'm doing. This, the derivative of the nth tetration of x, which we called tau n of x, was equal to two different forms that we had. We had the final version that we derived, which was the nth tetration of x divided by x log x times the sum from k equals 1 to n of the product from m equals k minus 1 to n minus 1 of the nth tetration of x times ln of x. Based on this thing we just proved, this expression for the derivative of any power tower, any integer power tower, we're going to explore what this might be. What is the derivative of the nth tetration of e to the x? Well, this is quite simple. And the reason it's quite simple is because the derivative of this is going to be identical to this expression, but two things will change. We will have to plug in e to the x wherever we see an x, and then we have to also multiply by the derivative of e to the x, because that's how the chain rule works. And so we actually end up with an even nicer expression than this, which is hard to believe, because this is quite a pretty expression, even though complicated though it is. So let's simply do that, right? So we plug in e to the x wherever we see an x, so we have the nth tetration of e to the x divided by, x gets replaced by e to the x, and ln of x gets e to the x plugged into it. And then we have the sum from k equals 1 to n of the product from m equals k minus 1 to n minus 1 of log of e to the x times the nth tetration of e to the x. But then, of course, because we're applying the derivative, we also have to multiply by the derivative of e to the x, which is e to the x. And lo and behold, look what happens. The e to the x is cancel. Ln of e to the x is just x. Ln of e to the x is just x. And then look what we have inside this product, amazingly. We have x times the nth tetration of e to the x. Well, by golly gosh, that's just the nth epsilon function. Isn't that beautiful? It's just the nth epsilon function. It's very lovely. Very nice. And what we're going to do, actually, is erase all this extra junk. Right? We have this x in the denominator. Right? And now we're simply going to multiply both sides by x. Like so. And I'm not going to cancel these x's. What I'm going to do is I'm going to rewrite this as, well, this is the nth epsilon function, of course. Right? I hope that's clear, right? The definition of the epsilon functions that I gave in the previous part was x times the nth tetration of e to the x. So as it turns out, this expression, x times the derivative of the nth tetration of e to the x, is equal to the nth epsilon function divided by x times the sum from k equals 1 to n of the product from m equals k minus 1 to n minus 1 of the nth epsilon function of x. A very, very nice function, very nice expression indeed. But remember, what was this? Doesn't that look familiar? Because I asked about this earlier on in this video. I said, we're going to want to know how to express this particular term. Because remember, if we looked at the derivative of the nth epsilon function and wrote it as x times the nth tetration of e to the x, we showed that this was equal to the nth epsilon function divided by x plus this precise term, x times the derivative of the nth tetration of e to the x. Which means we can just replace this with this expression right here. And we will be able to put the derivative of the nth epsilon function entirely in terms of other epsilon functions, which is just amazing. So we just have to replace this with this, because they are equal. So let's do that. We notice that because we had this term out the front, and then we have plus this stuff here, we can factor this epsilon n of x over x out of both of them, right? And sort of factor it out. So the first term we have inside this new factor is 1, because remember we just had this as the first term, and then plus this stuff here. So plus the sum from k equals 1 to n of the product of m from m equals k minus 1 to n minus 1 of epsilon m of x. So we have a beautiful expression now for the derivative of the epsilon functions now, which it's just stunning. It's just a gorgeous expression. So let's take a look at one of the simplest ones, which would be the first epsilon function, or x times e to the x. So we're taking the derivative of x times e to the x, which is the first epsilon function, and we know it's got to turn out to be e to the x times 1 plus x. So let's hope that that's what happens. So we simply have to plug in 1 wherever we see an n, right? So we get, and by the way, we don't have to prove this one with induction now, because A, we proved that the derivative of the tetration function was this, and then we just applied it to what we know about the epsilon function. So this is absolutely true. This is 100% the case. So we just have to plug in 1 for n, like so. And the first epsilon function is x times e to the x, so x times e to the x over x just gives e to the x, and then we have 1, but now this sum only goes from 1 to 1. Plugging in 1 for k, we get 0, so it's a product that goes from 0 to 0, which means it's just 1, and the 0th epsilon function, which means it's just one term, and the 0th epsilon function is x, and so we do in fact end up with the correct derivative, and it works out in the end, which is just lovely. And now for the last thing that I want to do, deriving general formulae, even though I have one cool surprise at the end that I think will titillate people. So the one last thing we wanted to derive was, of course, the derivative of the arbitrary omega functions, which are the inverses of the epsilon functions. Now, because of the way derivatives of inverse functions go, I know that this has to be equal to 1 divided by the derivative of the nth epsilon function applied to the nth omega function. And I said that before, and I proved it in a previous video of mine. So all I have to do is reciprocate this and plug in, wherever I see an x, omega of n of x. So if I just reciprocate this, I end up with x, so I would replace that with omega n of x, divided by epsilon n of x, but now I have to replace the x with omega n, so I get epsilon n of omega n of x. But of course, what's epsilon n of omega n? Well, they're by definition inverses, so they just cancel each other, and I'm just left with x. And I still have here the sum from of 1 plus, or I'm sorry, the quantity in the denominator now, because all of it got moved to the denominator, of 1 plus the sum from k equals 1 to n of the product from m equals k minus 1 to n minus 1 of epsilon m of omega n of x. So all of these epsilons, because they only go up to n minus 1, will not be the inverses of this epsilon n function. So it's kind of, strange, right? In this one instance here, they cancel and you just get x. But in all the other cases, the epsilons are too small to cancel the omega function. So perhaps someone might want to explore the properties of lower epsilon functions applied to higher omega functions. Maybe there's a neat relationship there that I don't know about. And so we actually have 3 amazing derivatives that we've derived today, or general derivatives based on functions that we've discussed in the previous part. And of course there was the tetration derivative as well, which is up here. Just beautiful results. Stunning expressions. Of course, this is more the main crux of the argument because the others are derived from that. But ignoring those for right now, let's discover something really quite amazing. Because remember, these work for any finite n. But let's just throw caution to the wind, and let's do what we did in the previous video and see if there's a way we can define a relationship of the infinite cases, where n goes to infinity, which would make these infinite sums and products. So let's take a look at that with regards to the omega function, because I think that's probably the most elegant looking one. And so all we're going to do is just simply let that n index go to infinity and see what we get as a result. Really something quite nice that I think is going to, people are going to appreciate it. So remember, what was the limit as n goes to infinity of omega n of x? Which was, in particular, we called it maybe omega infinity of x, or maybe just omega of x, since that was never taken. It turns out that this was precisely equal to x times e to the negative x, which is the same as negative epsilon 1 of negative x. Very neat relationships. This is all just notation. These are what the functions actually are. This is what the function actually is. So if we take the derivative of this, this should be the same as plugging in infinity into that formula for the nth derivative of the derivative of the nth omega function. And let's see if that, let's see what that gives us. So we know that the derivative of omega infinity should be omega infinity divided by x times the quantity 1 plus the sum from k equals 1 to infinity of the product of m from m equals k minus 1 to infinity of epsilon m of omega infinity of x. But remember, omega infinity is not this obscure function. It's precisely x times e to the negative x. We were able to derive that. So this is actually going to be a derivative of a very simple function. So if we just replace all these things, so we're going to have the derivative of x times e to the negative x, which is going to turn out, and I'm sure you can derive on your own, to be e to the negative x times 1 minus x. That's going to be the derivative. And this expression will have to be equal to that over some radius of convergence. I don't know if it converges everywhere. I doubt it very much. But it will. It either doesn't converge anywhere or it converges somewhere. The point is, it's an interesting derivation nonetheless. So now we have to replace every omega infinity that we see with x times e to the negative x. So we get x e to the negative x in the numerator, and we get x in the denominator, and then we get the quantity 1 plus the sum from k equals 1 to infinity of the product from m equals k minus 1 to infinity of omega m, epsilon m of omega n, not omega n, of omega infinity of x, which is again just x times e to the negative x. So that's what we've derived so far. The amazing thing is this. Because these two things must be equal, I can cancel the e to the negative x's, I can cancel the x's, I can reciprocate both sides, subtract that 1 over, and we end up with the result that 1 over 1 minus x minus 1, because this 1 will get subtracted over after we've reciprocated both sides, which is the same thing as x over 1 minus x. This is equal, somehow, to the sum. I need to put this result on its own. So we have 1 over 1 minus x minus 1, which is the same as x over 1 minus x. This is equal to the sum from k equals 1 to infinity of the product from m equals k minus 1 to infinity of the nth epsilon function evaluated at x times e to the negative x. And I think that's just stunning. I mean, think about that. We've been able to reduce such a complicated set of functions that are just these obscure symbols being thrown around, like crazy, into such a cool relationship between such a simple function, x divided by 1 minus x, and be able to somehow express it as this infinite sum of an infinite product of these completely wacky e to the x power tower functions in the most complicated way. But if you plug this into Desmos and you start typing out, obviously you can't do all infinitely many terms, but if you start typing out the first few terms, letting n be like 5 and then typing out the terms that you would get, it wraps around this function perfectly. It's absolutely amazing that that's true. And you can do other things. You can replace x with the inverse of this function here. Because this is omega infinity, we can replace everything with epsilon infinity, and we get epsilon infinity of x divided by 1 minus epsilon infinity of x. And then we just get x in here, right? Because this is omega infinity, so the epsilon infinities cancel. But what is epsilon infinity? Epsilon infinity is actually, right, it's the inverse of this. So if we do the limit as n goes to infinity of epsilon n of x, we'll get epsilon infinity, or perhaps just epsilon of x if we wanted to write it that way. And we'll end up with negative omega 1 of negative x, or negative Lambert W of negative x, because they're the same thing. So in this case, we'll actually end up with negative omega 1 of negative x divided by 1 minus negative omega 1 of negative x. And those negatives will cancel, of course, etc., etc. But we'll, of course, end up with this beautiful expression because omega infinity and epsilon infinity cancel, and we just get the sum from k equals 1 to infinity of the product from m equals k minus 1 to infinity of epsilon m of x, which is just stunning, just beautiful. Truly lovely. And there's a similar relationship you can derive with the tetrations, the infinite tetration, but it just sort of ends up being a garbled mess with a bunch of logarithms flying around, and it's not as interesting as these two expressions, I don't think. We can simplify this by simply writing 1 plus omega 1 of negative x. Just two stunning, stunning results. And this is as far as I wanted to go today. You talking about the derivatives of these functions, I think I've probably talked enough. Try plugging this, especially this, into Desmos. It really does work. You can do this one as well. All you need to do is plug in the integral representation of the W function that I proved in the Wacky Calc Wednesdays that I've been doing lately. These all do, in fact, tie into each other. So thank you for watching this video if you have. I would like to just make sure, just before we go, that I hope that's clear. Bring it, Papa. Generalize that. Part 3 may be coming.